Calculus 1, you learned that you could find the area under a curve, or the area between the curve and the x-axis, by using integration. In this lesson, we're going to extend that concept and find the area between two curves. So we're going to start with this example. I've got a curve here, f of x equals x squared plus 2, and this linear function, g of x equals negative x. We want to find the area between these two functions between x equals 0 and x equals 1. So we're going to find the area of the region. The area is equal to the integral from a to b of the top function, which would be the x squared plus 2 minus the lower function, which is negative x. Okay, I can combine these two functions, and I know that my limits are going to be from 0 to 1, x squared plus x plus 2 dx. Now I can integrate each one of these terms separately. So x squared becomes x cubed over 3 plus x squared over 2 plus 2x evaluated from 0 to 1. So this is going to give us 1/3 plus 1/2 plus 2. Those are the values at 1. The values at 0 are all going to work out to 0, so we don't need to even subtract those. And when we add these together, we get 17 over 6. So that is the area between those two curves, or those two functions. In our next example, we're going to look at two functions that intersect. And those are shown here. G of x is equal to x, and f of x is equal to 2 minus x squared. So very similar to the last problem in terms of the functions. So since f of x is on the top, we'll put that first. 2 minus x squared minus the g of x, which is just x, dx. Okay, we weren't given limits of integration, so for this problem, we need to find these intersection points. Okay, one of the reasons I like to draw a sketch graph for all of these problems is because sometimes on the sketch I can see where those intersection points are. And just a real quick calculation tells me that these intersection points are at -2, -2, and this point is at 1, 1. So taking the x values of those, I know that I'm going to integrate from -2 to +1. I'm going to rearrange these a little bit so they're in order. Negative x squared minus x plus 2 dx. Okay, once again, I'm going to integrate. So I'll have negative x cubed over 3 minus x squared over 2 plus 2x and I want to evaluate from -2 to +1. Okay, and when I do that, I end up with 9/2. Okay, so that's the area of that region. In our next example, we're going to find the area between two trig functions, sine and cosine. So here's my sketch graph. And if I remember a little bit about trig functions, I know that this point where sine and cosine are the same is pi/4. And the next point where sine and cosine are the same is 5pi/4. So these are going to be my limits of integration for this problem. Okay, this curve here is sine, and then the other curve is cosine. So my integral is going to look like this. The area is equal to the integral from pi/4 to 5pi/4, and we'll use the top curve first. So that's going to be sine of theta minus the lower curve cosine theta d theta. And we'll use theta for our variable since we're looking at trig functions. Okay, and now when we integrate this, it's very convenient to have our reference for integrating sine functions or trig functions to make sure that we get the signs right. The integral of sine theta is negative cosine theta, and the integral of cosine theta is sine theta. And again, we're evaluating from pi/4 to 5pi/4. Okay, and again, we can kind of look at our graph and recall what those values are. So at pi/4, cosine theta is, at 5pi/4, which is where we're starting. The cosine is negative √2/2, but we had a negative here, so that's a negative. Sine is also √2/2. And we were subtracting that, but it was also negative. So we've got that. Now we need the values for pi/4. And we're subtracting those from these values. So now cosine at pi/4 is √2/2, but we want the negative of that. And then we're subtracting the sine of pi/4. So √2/2. Okay, so this ends up being the square root of 2, negative square root of 2, but we're subtracting, so this is positive square root of 2. Same thing applies here. We're going to get square root of 2. And we end up then with 2 square root of 2. Okay, this is one of the reasons that I asked you to come up with a little reference booklet for yourself for some of these integration rules. It's very easy to make a sign mistake and get the wrong answer. In our next example, we're going to look at a situation where two graphs cross each other multiple times. In this example, we have a cubic function here, 3x cubed minus x squared minus 10x, and a quadratic function here, negative x squared plus 2x. Because there are the multiple intersection points, we're going to have to integrate this in two different parts. We'll start with the region from negative 2 up to 0 and integrate that. And then we'll integrate the section from 0 to positive 2 and add our results together. So let's get started with the first region. We've got an integral and we're going from negative 2 to 0. And in this section, the cubic function is on top, so we'll start with it. 3x cubed minus x squared minus 10x. And then we're going to subtract this quadratic function. Well, the x squared was already negative, so we're going to make that plus x squared and then minus 2x dx. Okay, I'm looking now for like terms that can be combined. I see I have a negative x squared and a positive x squared, so those can be eliminated. I have a negative 10x and a negative 2x, so those can be combined, which makes my integral from negative 2 to 0 of 3x cubed minus 12x dx. Okay, integrating gives me 3x to the 4th over 4 minus 6x squared. And we're going to evaluate from negative 2 to 0. Which gives me negative negative 12 minus 24. So this comes out to positive 12. So I'm just going to make a note for myself that the first part of my answer is positive 12. And now we're going to do the second part of this integration. And for the second region, we can see that the quadratic function is on top. So we will list the quadratic function first. So there's our negative x squared plus 2x. And now the cubic function, we're going to subtract 3x cubed minus x squared minus 10x. Okay, and again, this time we're going to go from 0 to positive 2. Okay. Once again, I can see that this negative x squared is going to cancel out with this one because it was a negative and a negative. And then when I put my terms in order, I get negative 3x cubed. And I have a plus 2x and a negative, so plus 10x, so plus 12x dx. And you're going to see this answer comes out very similar. I know that the values at 0 are going to be 0. So I just look at the values at 2 after I integrate. And when I integrate, I get negative 3x to the 4th over 4 plus 6x squared. And again, from 0 to 2, but I don't need to worry about the 0 part, so just the 2. So this is going to be negative 12 plus 24, which gives me positive 12. I have my positive 12 from the first part, so I just add those together for a total area of 24. In our last example for this section, we're going to look at something that's a little bit different. We're going to be looking at this area, which is defined by a linear function, but then by a quadratic curve that is not a function because it's been turned on its side. Okay, there are two different ways to approach this. We're going to look first at integrating with respect to y instead of with respect to x as we've done before. So writing my two equations in terms of y, I get f of y is equal to y plus 1, and g of y is equal to 3 minus y squared. Just as we have done before, we need to find these two intersection points. From my graph, I can see that this point is at -1, -2, and this point is at 2, 1. Because we are integrating with respect to y instead of with respect to x, we'll be using these y coordinates as our limits of integration. So let's write the integral. We've got areas equal to the integral from -2 to +1. And since the g of y is on the right, which would be the larger part, we'll write that first. 3 minus y squared. And then we will subtract from that the f of y, y plus 1, dy. Okay, simplifying, we get this, negative y squared minus y, and now I have a 3 minus 1, so plus 2 dy. Now I integrate just as if I was integrating with respect to x. So I'm going to have negative y cubed over 3 minus y squared over 2 plus 2y, not dy. And we're going to evaluate from -2 to +1. Okay, starting with 1, I'm going to get negative 1/3 minus 1/2 plus 2, and I'm going to subtract my values for -2, which are going to be 8 over 3, and I've got -2 squared over 2, so that's 2, and 2 times -2 minus 4. Okay, simplify that all out, and I end up with 9 over 2. I'm going to make a note of that 9 over 2. That's what I got when I integrated with respect to y. So I'm just going to write that over here. when I integrated with respect to y, I got 9 over 2. And you might wonder, well, why do we integrate with respect to y? Why don't we just integrate with respect to x like we've always done? Well, let's take a look at what that would look like. Well, you might be thinking, why can't I just integrate with respect to x? That's what I've done before, that's what I'm used to. I think it would be simpler. Well, let's take a look and see. If I want to integrate with respect to x, I do have one challenge. And that's that in this part of the region, I have the linear function on top and the square root function underneath. But once I get to this point at 2, 1, I have that square root function on both the top and the bottom. So I'm going to have to do 2 separate integrals with respect to x. Let's get started. Okay, I have to rewrite my equations also in terms of x. So the linear equation will be y equals x minus 1. And for the quadratic part, which is actually a square root, I'll have y equals negative square root of 3 minus x. Okay, for this first region, my limits of integration are the same as they have been, using the intersection points, negative 1, negative 2, and 2, 1. And since I'm going to integrate with respect to x, these will be my limits of integration, the x coordinates. So the area for the first region is the integral from negative 1 to 2, and then I start with the linear x minus 1 and subtract the square root, which is negative square root of 3 minus x dx. Okay, I'm going to rewrite this with a rational exponent. And since I have 2 negatives, this will be plus. It's going to be 3 minus x to the 1/2 power. Okay, integrating, I'm going to have x squared over 2 minus x minus 3 minus x to the 3/2 power over 3/2. And if you don't like that fraction in the denominator, we can change that and write it this way, 2 over 3. And we're going to evaluate this from negative 1 to 2. So at 2, I've got 4 divided by 2, which is 2, minus 2. And then when I put a 2 here, I'm going to get 1 to the 3/2 power, which is just 1. So I have minus 2/3. Okay, and these 2's are going to cancel out. Now I'm going to subtract the values at negative 1. So this is going to be 1/2. This is going to be plus 1. And then this part, when I put negative 1 in here, I get 4. 4 to the 3/2 is 8, so I have minus 16 over 3. Okay, let's simplify this. I have 16 over 3, positive 16 over 3, since there's a negative here and a negative here, minus 2 over 3, so that's going to be 14 over 3. And then I've got a 1/2 and a 1, so that's 3/2 minus 3 over 2. Okay, if I want to change that, combine or get a common denominator, I'd have 28 over 6 minus 9 over 6 would give me 19 over 6. So I'm going to make myself a little note that for the first part of the area, that first region, region 1, 19 over 6. Okay, now I still have to integrate this region from 2 to 3. So that area is going to be the integral from 2 to 3. And I can see that the upper part and the lower part of this region are the same. It's symmetric. So I'm just going to put a 2 here and find the integral of just the top part. Again, 3 minus x to the 1/2 power dx. Okay, when I integrate, I end up with negative 2 times 3 minus x to the 3/2 power divided by 3/2 evaluated from 2 to 3. Okay, when I put the 3 in here, this becomes 0, so the whole thing is 0. When I put the 2 up here, I have 1 to the 3/2 power, which is 1, divided by 3/2, which is going to give me just 2/3, times the negative 2 is negative 4/3, but I'm subtracting, so it's positive 4/3. Okay, now I'm going to add my result from the first region, which was the 19 over 6, plus the result from the second region, change this to 6, and it's 8 over 6. So I end up with 27 over 6, which I can reduce to 9 over 2. Okay, and I can see now that integrating with respect to x, I got the same answer as integrating with respect to y. Okay, so this is one thing you can do to check your work on some of these problems. And I think most of you would agree that integrating with respect to y in this case was easier since I only had to integrate one time. Okay, this is the last example I'm going to work for this section. Again, check your Blackboard for a link. Some of your homework problems ask you to verify by using a graphing utility. I don't have the software I need to show that to you, so I'm going to put a link in Blackboard for a YouTube video that does that. And hopefully I'll get that graphing utility pretty quickly and be able to show that to you in the future.